taught by Marta Mazzocco, and the title is Quantum Uniformization and Calabi-Yau Algebras. So Marta, I give you the floor.
Thank you very much. Yes, this talk is based on a paper that we wrote together with Leonia and Volodia. So if you have any questions, please ask, and if I can't answer, ask them. Okay, so I will start with a little bit of a motivation for this story, which comes out of mirror symmetry. So in mirror symmetry, you have two sides, the so-called A side and B side. On the A side, one has a pair, which is called a Loyenga pair or Calabi-Yau manifold variety. Sorry. So Y is generally a smooth projective surface. And D is a divisor on this surface. On the other side, we have a...
sorry, Marta, so Y is a complex surface, right?
Projective, yes. Mm-hmm. Yes, yes. Oh, sorry. Yes, for me, life is complex, okay? Always.
Okay, well, good to know.
Huh?
Good to know. Thank you.
Yes. Yeah. Okay, and so on the other side, we have a flat family of surfaces, which will be the spec of a ring structure on a certain vector space. So the mirror symmetry essentially is a way to associate to one side the other side and vice versa. Roughly speaking, on this side, we will have a natural symplectic structure. And whilst on this side, we have a complex structure. And so what we are interested in is quantization. And in particular, on this side, what we have is that this will be geometric quantization. Whilst on this side is deformation quantization. So another thing I wanted to say, so in the left side, this is where naturally Gromov-Witten theory is developed. And if you like, this is where Donaldson-Thomas theory is developed, or Landau-Ginzburg, okay? So what I want to do today is to discuss a special set of surfaces which can be sitting on both sides, okay? Okay, so these surfaces have a special form. They are, did I say everything I wanted? Yes, they are, so they are zero sets of a certain polynomial. So we will take zero sets, I will denote them by n phi, and this will be the set of phi of x1, x2, x3 equal to 0, where phi has a very specific form, namely phi will be given by a triple term, x1, x2, x3, xi are in the complex. And then there will be the sum of three terms, each of which is a polynomial in one only of the variables. Okay. So let me, so these surfaces are affine del pezzo surfaces. And let me give you some examples where you might have encountered these surfaces, because they actually appear in many areas of mathematics. So here I've made a list of examples. So one example is the moduli space of Sclianin algebra with 4 generators. This means that you have Sclianin algebra is generated by 4 generators and relations. There are some constants in those relations that appear. Let's denote those constants by x1, x2, x3. in order for the Sclianian algebra to satisfy things such as the Jacobi identity, then you need to sit on the zero set of such polynomial, which has exactly the form we like. So we have only one mixed term and then 3 terms in one variable. There is also in singularity theory, polynomials of this sort appear both in standard Duval singularity, but also in elliptic singularity. So for example, flat deformations of the E6 Twiddle elliptic singularity are described by a polynomial of this form. So you recognize here the Hesse cubic, if you like, and then some deformation to it, okay, where these eta are and omegas are some constants. For Leonia specifically, this example, we have the SL2 character variety of a torus with one boundary. And we have also the character variety of a Riemann sphere with 4 holes. Okay, so they appear in many, many ways. And in particular, today I would like to talk a little bit more about the very last example. So this guy, because this guy is interesting from the point of view of mirror symmetry. Recently, it has been proved by Gross, Hacking, Kiel, and Siebert. So they put a paper dedicated just to this specific cubic to prove that it's self-mirror. So let me maybe explain a little bit about this. Gross, Hacking, Kiel, and Siebert. I think they put this paper in sometime in June, maybe. It's for Miles Reed's birthday. Anyway, okay, so let me explain to you a little bit in what way this, this specific cubic appears both on A side and B side. So on the A side, what we need a Loyenga pair. So we need a Y, which is a smooth surface in P3. Well, this is the zero set of the completion of this polynomial. So let me write maybe with a straight symbol phi in homogeneous coordinates z0, z1, z2, z3. So this is the polynomial of z1, z2, z3. So I'm just literally taking the standard procedure to make this polynomial homogeneous, sorry. Okay, so I multiply the quadratic term by z0, I multiply the linear term by z0 square, and the constant term by z0 to the cube. Okay. So Y is the zero set of this homogeneous polynomial, therefore Y is a surface in P3, which I have taken with the homogeneous coordinates. Okay. What is the divisor? The divisor in this case is given by the triangle of lines Z1, Z2, Z3. Okay. This is a triangle of lines because we are in projective P3 space. Okay, so the A side is pretty simple. And so what is the B side for this story? The B side, we have a family of, as I said, we need a flat family of surfaces. So, and phi, this is our zero, phi equal to 0 in C3, our affine del pezzo. We can think of it as a family on C4, where C4 is the space where our parameters vary. Okay. Let me just show you again this cubic. We have parameters here. So for every value of this point in the C4 space, we have one surface, the pezzo surface. So in general, we'll have a family. And so for each point in C4, we have such affine surface, which is an affine cone. on the P2 surface, which corresponds to the divisor. So now I'm looking at this divisor as a subset in P2 with homogeneous coordinates, in this case, x1, x2, x3, okay? So this is a fine cone, and it has a trivial line bundle, which is simply, well, the same itself minus the point 0. And the ring of sections is the sum of, let me call this surface in our paper, we call PM5. So this is PM5, phi L. Oops, sorry. Okay. So not okay. Okay. And this is in fact roughly the same thing as if we look at the ring of polynomials in 3 variables and take the quotient by the ideal generated by phi itself. Okay? So what I'm going to do today. Today we are going to give a quantization of this object here, of this ring, of the ring of sections. So in the gross hacking and kills situation, the elements in this ring of sections are the so-called theta functions. So I should call gross hacking and kill theta function. So what I'm going to do is, by describing a quantization of this ring, we actually giving some, if you want, some description of the theta function in the non-commutative world. Are there any questions so far?
Sorry, maybe I still haven't quite got it. So what's the family on the B side?
Let me give you the example because, oh yes, it's very simple. So yes. Let me show you.
Yes.
So we have this cubic, right? The cubic is, the cubic is the 0 set. Mm-hmm. So this family is the 0 set of certain cubic, but this cubic depends on some parameters.
Yes, but on the left, on the A side, the cubic has some fixed parameter. Is it right? On the A side, we don't consider the family. We have a concrete cubic with some concrete omega 1, 2, 3, 4. Is it correct?
But, no, I can still consider a family.
But then what you said in the beginning, on one side we have a surface with a divisor. On the other side we have a family. Does it still hold? Because I get confused about the setup, right? In the beginning, you presented a very clear setup, but now are you changing it?
No, I'm thinking. Let me. Okay, I don't know now. I have to think.
Okay. Okay. That's a good answer.
Yes, I will think. Yeah. Usually when I'm giving a seminar, my brain doesn't think. So maybe you will receive an email 5 minutes after I finish the seminar and say, oh, that was stupid of me.
Yeah, no problem. Don't worry. Let's proceed.
Yeah, sorry about that. Okay, let me also open the window because it's actually hot. Okay. Sorry. Okay, let's keep going. Are there any other questions? You can ask questions. The worst that can happen is what happened with Anton. I'll say, no, I don't know. Okay. Right. So essentially what I'm going to do, as I said, is to present some quantization of this ring of sections and in a broader context. And I should have said that in this example is especially pretty because this specific cubic is a self-mirror.
Can I ask a question, actually?
Sure.
I'm confused a bit about the relationship between m phi and p m phi.
Oh, okay. So m phi is the zero set of the polynomial phi in C3.
Yeah, and the polynomial is which one again?
It's this polynomial. So when I take the zero set of this polynomial, I have a set in C3, okay? Phi equal to 0 is a set in C3. That's why this is an affine del pezzo surface. Now, when I complete projectively this surface, so let me call this surface m phi, I can complete it projectively, which means I take it as a surface in P3, and then this is the equation of that surface in P3, in homogeneous coordinates in P3, okay? Mm-hmm. But I can also do something else. I can say, let's take this part, okay? This is the divisor of my del pezzo. See, it's the divisor here, because when I take z0 equal to 0, then I restrict to d infinity, which is given, so I restrict to, sorry, to d, which I've already written here.
You mean when you take m phi and you just look at the boundary that you added on, it's exactly going to be this?
Excuse me?
When you add on the boundary of m phi, then
yes.
The boundary is exactly
Yes. So, and this is my divisor. I've written it in P3 here, okay? So I should have, okay. Now, however, I could also think about it in a different way. I can look at it in C3, and I can think of this x1, x2, x3 equal to 0. I can think of it as something which is written in P2, because it has only 3 coordinates, homogeneous. So I can think of it as in P2. So this guy is precisely that, as, so it's the P2 curve which comes from that divisor.
It's the boundary of m phi.
Yes, but if you, yes, okay, if you want to think of it that way, intuitively speaking, yes.
Right, it's not the same as projectivizing phi. Is that right?
No, because what you mean by, okay, so when I projectivize, I go up. I am completing, doing projective completion. And here I am just taking, essentially I'm destroying all the deformation that I've done. So the one thing you can think of is to say, we have some undeformed quantity, which is this triangle of line. And then to this triangle of line, we attach some extra terms, okay? But if I remove them, I'm left with something which can actually live in P2. It's a curve in P2, okay?
Okay, thanks.
No problem. Actually, it's a very good question what you ask, because let's go here. Let me just say this, because it will be important. In the case of the flat deformation of the elliptic E6 singularity, my undeformed object is this one. So again, this is an elliptic curve, in this case in P2. But when I deform it, I'm adding terms, which are here. And we see that in order to make this projective, we need to go up 1 dimension. Okay? Okay. Okay, so as I said, this is a self-mirror, which even confuses maybe Anton a little bit more, because a self-mirror means that for every choice I make of y with fixed parameters, there is a family of curves, but then I change my y and then I get yet again the same family of curves. So in this sense, it's a family also on the left in this case. Okay. All right. Okay. So, so we are going to provide a quantization of this ring, and and in a broader context. So this broader context will also contain some other structures, such as Sgliani algebra and many other things. So I will get there eventually. But before I do that, let me perhaps list what we know so far. What is known about the quantization of essentially this kind of rings that we have, the ring of polynomials in 3 variables quotiented by some ideal. So there are works by Ettinghoff, Oblonkov, and Rains. Well, maybe I should write the names instead of and Rains. And they introduced some weighted projective del pezzo surface with nodal divisors and quantize them. So then there is a paper by Ettinghoff and Ginsburg, which speaks about Calabi-Yaus, Ginsburg, in which they also treat these elliptic singularities, of which I gave an example before. So here I gave the example only of E6, but actually they do also E7 and E8, and offer a quantization for. Then there is a work by Oblonkov in which he finds quantization, shows that the quantization of this guy is in fact the spherical subalgebra of double finite algebra of rank 1.
So sorry, Marta. What does it mean, quantization in this context? A non-commutative algebra with some parameter which would be a kind of flat deformation of...
I will show you. Okay. So essentially, the story is a little bit... there are like 2 deformations. So you see, in the context of what I was telling before to Francis, we have an undeformed part, which is this divisor. Then we have a flat deformation in some sense, okay, which is this tail. So in singularity theory, this corresponds kind of to the versal deformation of the singularity, if you like, okay? But then we want to quantize, which means that we will go from a Poisson algebra to some non-commutative algebra. And we want to do that in such a way that also at quantum level, everything is flat. Namely, in the quantum story, we will have the quantum analog of this part and the quantum analog of the flat deformation. And it will all be matching.
Okay. Is the Poisson bracket fixed, or are
I'm going to show you what is the Poisson bracket. Okay. Yeah, there is a very natural Poisson bracket on this stuff. Okay. All right, so let me in fact come to this. But before I do that, because I wanted to say that there are some things I want to say about this example of Gross, Hacking, and Kill. So here I wrote the example again. So this is, and Siebert, sorry, I forgot Siebert. This is the example of Gross, Hacking, and Kill and Siebert. And so in my world, this is the monodromy manifold of the Pandey 6 equation. So, and there are many other Pandey equations, which we can obtain from the 6th Pandey equation by some confluence. And here we have listed all the corresponding monodromy manifolds. And as you can see, they all have the same form. So I've written here the general form underneath. So they all have a triangular term. So all of these are, if you like, the flat deformation of a triangle, okay, in P2. The triangle is in P2 and then we deform in P3. The number C, the top one has the coefficient equal to 1. So this number epsilon can either be 1 or 0 as you go down the list. As you can see, for example, here epsilon 3 is 0. Here all the epsilons are 0, okay? And so they all have the same form. And for us, it was important that the quantization procedure we obtain is compatible with this confluence. And this is not at all trivial because it's a degeneration, but I will show you what that is. I wanted just to mention this motivation, maybe if there is somebody who is more interested in integrable systems, and that was what was on the back of our mind. So I would like maybe to spend a couple of words on some geometry as well here. So I mentioned already that this cubic is also the same as the character variety SL2C character variety of a Riemann sphere with 4 holes. And as we go down this list, what we find are some special subvarieties. All of these guys are subvarieties of another object, which we called cusp character variety. And this is important because cusp character varieties have a natural structure of cluster algebra. So I think it's interesting for that reason, because then we can also quantize the cluster algebra and compare. So let me just give you one example before I move on to this quantization. I want to discuss a little bit this example and explain what it means that it's a subvariety of an object which is called cusp character variety. Okay, so maybe in this example, so the basic example is that we imagine that we are dealing with some linear system in which there is this linear system of differential equations in which there are higher order singularities. So we want to consider a linear system in which we have a singularity of Poincaré rank 1 at infinity. So this means that at infinity we have a pole of order 2. So if you study the monodromy of this system, you will find that at infinity you have what is called the Stokes phenomenon. Namely, you cannot define solutions in disks anymore, but you will be only able to define them in sectors, okay, of this form. So with Chekhov and Rubtsov in a previous paper, we proposed to describe this situation by associating, instead of a standard character variety, associating to this system a Riemann sphere which has 2 holes, namely the hole due to the term z equal to 0 is 1 hole, okay? And another hole comes from z equal to 1. And then we have a third hole, which is due to the fact that we have infinity is also a singularity of this differential equation, but somehow we want to keep in mind the fact that this singularity is irregular and it needs two sectors. So here we are with two cusps that somehow, if you like, encode the line which divides these two sectors. So these two lines, half lines. Okay, so to describe this character variety, decorated character variety, well, I can give you the definition. So essentially, we take a Riemann surface. It has 3 holes and 2 Stokes sectors. So we consider a groupoid of arcs of this surface and consider the representations. Okay, so I can take homomorphisms of this into SL2.
Sorry, you mean the groupoid of arcs, but the base points of arcs, they are fixed?
We fix them at the cusp. Oh, actually, I might have had a picture because I was prepared. Ah, yes, here it is. This was the picture I had at the beginning. So, for example, I can generate this groupoid by choosing. I choose one cusp like my boss, okay? So this is the boss cusp in this case. And then we generate all the arcs and they go around the Riemann surface and either come back or maybe they go back to the other cusp. Okay? So we take this groupoid of arcs and as I said, so we have we call it pi A of this Riemann surface. And we take the representations in SL2C. But then we want to quotient by some freedom of acting with a group that keeps these cusps fixed. And this is, in this case, we have the, so at every cusp, you will have the action of a unipotent Borel subgroup. Okay, so I will maybe tell you very quickly how to see this cluster algebra. I just wanted to say that these arcs satisfy cluster algebra, okay? And the way to see that is to represent our Riemann surface by a ribbon graph like this. This ribbon graph has 3 holes, okay? So the first one is here and the second one is here. These correspond to the 2 holes which I have here, okay? And then we have a third hole which is outside. And so the cusps represent these Stokes lines, and they are represented with open edges in our graph, okay? And all the lines, all the arcs that I've drawn into the surface appear as arcs in this fat graph. So for example, look at this one. So my boss cusp is the one on the bottom. And for example, let's look at the blue. Okay, so the blue one goes from the boss, goes around the hole number 2 and comes back. And in fact, that's what it does. It goes around the second hole and comes back. Okay. So this, as I said, these coordinates, which are the length of these arcs, they satisfy cluster algebra, and they satisfy a very nice Poisson structure, which is of cluster algebra flavor, which means it's purely quadratic. Okay, there is no linear terms, no constants, purely quadratic. And the example of the Painlevé 5 monodromy manifold is a specific submanifold, which is given by the functions x of a, b, c, d, and of the length of these 2 perimeters, G1 and G2. The functions such that they Poisson commute with E and with D. And when you do,
just to make absolutely clear, so the small Roman letters A, B, C, and so on, those are the traces of the holonomy along the paths?
well, not quite the traces anymore, because my action is no longer SL2C. Okay, so in that case, I would have the traces. In this case, it's what we call trace K. So trace K of a matrix A is the trace of A times a matrix, which is given by, so essentially, well, I don't want to go into the origin of this, but yes, these are your characters, if you like, right, in the character variety. So these are your functions which are invariant under the action of this group. Okay. And so these traces satisfy this Poisson structure, they satisfy cluster algebra structure. And then within this object, you have a special submanifold in which you request that the functions are commuting with E and D. So I wanted to say that ED, the product, is a Casimir, but not each of them individually. For example, look, E with B will give me BE over 2 as Poisson bracket. So that's not a Casimir, okay? So you are requesting a reduction here. Okay, so this is the way in which this specific example of this cubic, so what we find is that this is generated, in this case,
maybe I have a somewhat more general question. So how is it, so those Poisson structures and the variety itself, how is it related with various character varieties for higher order poles on the market, like with these bulge wild character varieties or with Leblanc Severa? Just to know, is it like
this is going to take me a long time to explain.
But maybe you just briefly say, is it the same or is it different, or what?
No, it's not the same. Well, okay, so the Severa one, it's on the space of representations, right? So you don't quotient yet. It's this quasi-Hamiltonian structure.
But it's up to you, right? You quotient or not?
Yes, well, so we quotient. So in a sense, you could say that if we don't quotient, we are roughly in the same picture. For the bulge one certainly is not the same, because his are much smaller dimension than ours for the same problem. Mm-hmm. So in the case of bulge, he finds directly the submanifold. So if you want, you could call this the wild character variety.
Mm-hmm. Okay, thank you.
Okay. And please don't ask me how to relate to the work of Marco, Gualtieri, and Pim, because I can't calculate their Stokes groupoid in the case of pi level 5, and so I can't tell you if it is or it's not the same. And I think we agreed that computation, I mean, we don't know how to do. Okay. All right. Anyway, so I just wanted to show why this, how these cubics arise, and the fact that they have a cluster algebra flavor, if you want. Okay. So just to give some motivation. So going back to the Poisson structure, so your previous question, we need to put the Poisson structure on this object. So let me go back to, going back to.
Could you just say what loops or paths E and D correspond to?
So E and D are these two.
Okay, thanks.
So they are the very special ones. And you see, the product of them is, in some sense, is homotopic to going around the hole. Okay? So pi level 5 essentially is telling you that it would like to be hypergeometric, but doesn't quite get there. So he would like to, pi level point level 5 would like to treat this loop around infinity as any other loop, like in the case of hypergeometric equation, but it can't. So that's the story of point level 5. Okay, right. Yeah, Poisson structure. So going back to the zero set of our polynomials of this form in C3, and what kind of quantization we do, let me first give you the classical picture, okay? So first of all, we quantize by deformation quantization a certain Poisson structure. Now the Poisson structure on surfaces of this form is very simple, and I'm sure everybody knows in this audience what I'm doing, but generally you can always take the polynomial which defines your zero set and then define the Poisson structure by taking partial derivatives of this polynomial. So we will have that x1 with x2 is d5 over dx3, and then the others one are cyclic permutations of this relation. This means that in particular, therefore, we have that as a Poisson algebra. Oh, sorry, I didn't say something important. I need to say something important before I say this. So as a consequence of this Poisson structure, in particular, you can prove that the polynomial phi is central, which means that this Poisson algebra descends to M5. So first you can endorse C3 with this Poisson structure, but then thanks to the fact that phi is a Casimir, you can make a Poisson structure on the zero set, on your affine cubic. So on this affine cubic, we have this pretty structure, and this structure is potential. Namely, we take this, you know, what we end up with is the space of polynomials. So as I was saying before, modulo the idea. And this algebra is a Jacobian. So the Poisson structure is given by a relation of this type. Okay? So we have a Casimir element, we have a Jacobian, and it's also unimodular. So essentially, because this Poisson structure allows us to define an over-vanishing volume form on M5. So it has all these beautiful properties. And now I will give you some quantization of this structure and then convince you that it's the right object to consider. Okay, so let me perhaps write explicitly down what is that we have in the case of our favorite object, which is phi equal to, I'm sorry, I will keep writing this forever and ever. I think they will put it on my grave if I keep doing this, but okay. We have, for example, that x1 with x2 is x1, x2 minus 2x3 plus omega 3 and cyclic. Okay?
Epsilon 3, x3, is it right?
Yes, thank you. My pen stopped working. Oh, what is it?
Yeah, but we know the answer. That's okay.
But I need the pen to finish the seminar. Sometimes it does that. Oh. 2 epsilon 3. Yeah. Okay. Thank you for this observation because I had forgotten my epsilons. Okay, so I will not explain to you how to obtain this quantization because it's a little bit long. But let me give you the formula, and then I will try to convince you that it's the right thing to do. I had this formula somewhere. Yes, let me bring it up. Oh, I want to. Allora. Sorry, I just want to try and bring it close to. Okay, all right. So let me give you this definition, and then I will try to convince you that it's the right object, okay? So we give this definition, we take the scalars epsilon1, epsilon2, epsilon3, thank you, Anton. We take Q, which is generic number, not a root of unity, and we define the universal Pandey algebra as the algebra which has now 6 generators. So we have the generators capital X1, X2, X3, which correspond to the classical variables X1, X2, X3. But we also treat the parameters as generators in our algebra. So in general, they will be operators. And the relations are that the operators omega I are central elements, okay? And then we quantize this relation in this form. So what we have is that the Poisson bracket is quantized to a commutator of operator, but because there is a quadratic term here, essentially we find the quantum commutator. Then we have the linear part, which will correspond to this term, and then the constant part, which corresponds to this operator omega 3. So the name universal is because, as I said, omega 1, omega 2, and omega 3 are considered to be operators. So, for example, in the case when all the epsilons are equal to 1, this is the universal Zhedanov algebra, which was studied, for example, by Terwilliger. So that's why we call it universal, and Pandey because it encodes all the cases of the cubics which arise in the Pandey theory. Now I could bore you, and I've erased it, but you know, we can take a semi-classical limit like is specified here, and if I do that, I could convince you that in fact you go from this quantum algebra to this Poisson algebra. I'm not going to do this computation. I suppose that it's pretty simple, but let me instead focus on why this should be true. I mean, I'm not proving the theorem, but I would like to at least show you that is true. So let me remind you that the classical algebra had 3 properties. So it was potential, it had a Casimir, and it was unimodular. So now we quantize, and we want to respect these 3 properties, okay? So I will show to you that these 3 properties survive, okay? And in fact, to do this, what I need to do is to specialize the algebra into by specializing the central elements. Namely, we take a quotient of this algebra UP. We take a quotient by assigning some values to these omega i's. Okay, this we call, how do we call it? Confluent Zhedanov. And this, for epsilon equal to 1, for all the epsilon equal to 1 is the standard the standard Askew-Wilson algebra, okay? So, and for this algebra, then we can prove that in fact, the algebra is potential in quantum sense. It has a central element, and it is Calabi-Yau, which is, in a sense, the quantum version of being unimodular. So let me show you what, I don't remember. Yes, I have the theorem here. So maybe I can move this again. Oh, sorry. This I'm trying to get used to this stuff, you know, it's not easy. So I try to get organized and then it's not working that well, but okay. Okay. So the theorem we can prove is that once we take the quotient, so what do I think about the quotient? Essentially, it will be the same algebra in which now the omegas will no longer be generators, they will be just numbers, okay? And because we will specify some values. So you can think about the confluence-Zhedanov algebra as the algebra generated by 3 generators, in which the relations are given in this form. And this algebra is potential. So it admits a potential, which I've written here. Okay. And it has a central element, which also is written here.
Marta, maybe 2 questions. For the central element, right, the relations, they all look quite symmetric under the cyclic permutations, but now the central element doesn't.
No, because you have to make a choice. Right, so the problem is this, that you have to make a choice. Okay, so first of all, let me remark 2 things. So let's look at the potential first, okay?
No, let's look first at the central element, because the potential, I don't know yet what it is, but okay. The central element, right, it's an element which commutes with everyone, is it right?
Yes.
And then the relations are completely symmetric, but you say you make a choice. What does it mean? I would understand the choice in the relations, and then, but now how could it be possible that the relations are symmetric, but then there will be many central elements?
Okay,
right?
Let me answer your question. So you see, I've chosen how to write this central element.
Oh, okay. Yes, okay. Thank you. So no that's just the writing of the first term.
Yes. So yes.
Mm-hmm. And my second question was probably what you were going to say. What does it mean, a quantum potential?
I'm getting there. So we need to define a derivative, okay? So what I'm going to say is that essentially the relations that I've written here, they are some derivative in some sense, cyclic derivative. So this is going to be that derivative, okay? And this is the phi over dx2, and this is, okay, I don't have space because when, okay? So, and these are cyclic derivatives. The way you take cyclic derivatives is by saying, okay, suppose I want to, for example, let's take the x2 derivative. What you do, you cyclically permute first in such a way that the quantity you want to differentiate is, for example, on the right, okay? So I need to cyclically permute. I will get x3, x1, x2 minus q. Now I will make a mess. Yes, x3. No, x1, sorry. That's why. Yeah, x1. Yes, x3, x2, okay, etc. And then you differentiate, which means that you essentially remove x2. Oops. Okay, so I'm to take the x2 derivative, I will differentiate this. And differentiating, once I moved my x2 to the right position, I just drop it.
In particular, Marta, this probably means that there is some PBW type statement, right? That
yes, it's coming, Anton. It's coming. Okay. Yes, there is a PBW statement. There are a lot of statements. I don't know if I'll get there, but yes, there certainly is a PBW statement. Let me just remark something before So interestingly, and the potential and the central element, once you quantize, are no longer the same. Okay, so this is typical, but for me it was, well, I wasn't used to this, and it took some while to understand it. The second part I wanted to say is, okay, so there is the theorem about the PBW. So let me give you two theorems, okay? So not only is potential and it is Jacobian, but as I said, it is Calabi-Yau. This is a family of Calabi-Yau algebras. And in fact, the point is that because, in fact, the way we prove it is that to prove that in the semi-classical limit, the Poisson algebra is unimodular. And this is a result due to Dolgushev, that when that happens, then your algebra is Calabi-Yau. And it is PBW. So it is a PBW deformation of the quantum polynomial algebra. Okay, so the quantum polynomial algebra you can imagine by the algebra which is generated by the similar relations in which we don't have these contributions. Okay, so you just lose this part, that's the quantum polynomial algebra, and then you have this PBW deformation, so it's a flat deformation of that polynomial algebra. Okay, now I realize that I've been a little bit longer than I wanted, so I'm not going to tell you anything about Daha. But I would like to at least tell you something about Sklianin algebra and how to see the algebra that I've explained so far and the Sklianin algebra in the same way.
Maybe let's negotiate the timing. So how much time would you need?
Maybe 4 minutes.
Oh, perfect.
Okay.
I was ready to give you 5, but well.
I said maybe. And I'm Italian.
Okay.
So, Italian together with maybe, you don't know what's going to happen, do you? Okay. Okay, let me tell you a little bit about what we want to do next. So what I'm going to do next is to take this algebra, take the Sklianin algebra, which I will describe in a second, and then create an algebra which specializes in some cases to the Sklianin algebra and in other cases to the this universal Painlevé or confluent Gedanov algebra. Okay, so let me give you a little bit about the Sklianin algebra. So this is the algebra. It's again, well, I denote the quantum polynomial algebra with the triangle brackets. So it's again a potential algebra, okay? So which is with some potential phi. And this potential is given by this formula. So we have our favorite term, cubic term, which when we quantize needs to appear twice. And then we have cubic now, cubic terms. So in the case of the Painlevé, we had square terms. Here we have cubic terms. And so if E0, E1, E3 are some points in an elliptic curve, then this is a PBW deformation of the polynomial algebra, of the quantum polynomial algebra. So what I want to do now is to give you kind of a mother algebra that contains the Sklianin algebra and the Pandey algebra as special limits. And so we define this generalized Pandey-Sklianin algebra, actually Sklianin-Pandey. And this is the algebra which is generated by x1, x2, x3. So every time I do some quantum algebra, I use capital letters for the generators, and the relations which are very a mixture. So we will have relations of this form, square plus then I'm sorry, I have to write them because I forgot to put this. I think I don't have this, do I? No, I forgot it. Okay. So x1, x3 minus beta, x2 squared plus b1, x2 plus b3. And then we have x1, x2 minus c, x2, x1 minus gamma, x3 squared. Maybe mistake here is a 2. Okay. So as you can see, I've written the relations. I haven't written a potential. And the reason is that if we pick values without any hypothesis, in general, this is not potential. And it mainly due to the fact that we have 3 different objects here, okay? So I don't know how to do a potential there, but we have a theorem which classifies. So what we're going to do is to classify all the values of all the constants that appear in this algebra in such a way that it is beautiful, namely it's potential, it is Calabi-Yau, it has a convergent Hilbert, Poincaré-Hilbert series, and it is also Koszul. Okay, so the theorem is that for a certain set of values, for either of the following cases, this algebra is potential. So let me tell you the cases. It's A equal to B equal to C, different from 0. And then we want that, oh, I never remember this. It's A cubed and alpha, beta, gamma, different from -1, 1. This is one case. Then we have A, B, C, not all equal to 0. And then we have some relations like and similar. So alpha is equal to beta, or we have gamma equal to alpha equal to C minus A, and so on, and similar. And then we have a third case, which speaks essentially the Pandey case, in which all these quadratic terms disappear, and A, B, C is different from 0, 0, 0. So in all these three cases, in all this specialization, this algebra is potential with an explicit potential. It is Calabi-Yau. It has convergence Poincare-Hilbert series, and it is Koszul. So it's a very...
But the first case is kind of generic, right? So
yes. 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 So generically it is, but you have to exclude some values. Well, it's not complete. You see, okay, I don't, not generic because
nothing is generic. Yeah, sorry.
We ask that A is equal to B equal to C. Yeah. So, but it's still interesting because this is essentially the Sklianin case, but we allow a deformation of this Sklianin. Okay. Then here I have the Pandey case. And here I have some sort of mid case in which we allow A, B, C generic, but then we ask some relations in the deformation. Okay. Now I don't have time, but I would like at least to show you a list. So what we did was to classify all the cases in which we have some nice algebra, which is Calabi-Yau, and also given that we wanted to have in mind this mirror symmetry picture and these divisors and so on. So we have a table, and I would like to show you this table because it lists all this stuff. So let me just, once I show you the list, you will understand what I'm getting to. So now, I'm sorry, the list, you see, it will be small on your computer screen, but let me at least give you a feel of this list, okay? I can't. So there are several objects in this list. So first of all, maybe not first, but in fact, this column is our polynomial phi, okay? So this is all the cases of the polynomial phi. And we start from the most generic, if you like, polynomial. Oh, sorry, I forgot 2. There's a 2 here. Okay. So here we have the polynomial phi. And here on the second column, so all of these guys are affine del pezzo surfaces. The zero set is an affine del pezzo surface. And here on this column, I have the divisor. So for example, in the first line, we have the Etinghoff-Ginzburg elliptic E6 surface, and the divisor is an elliptic surface, which is drawn here, okay? Then we go down. Here we lost one of the cubic terms. So the divisor has lost also a cubic term, and here we have the corresponding degenerated elliptic surface. And then we go down and essentially by going down along this column, we go down the Kodaira-Néron table, okay, with the divisors. The other part of the table is some, oops, sorry, some double affine algebra story. So let me use a different color. So we have a double affine algebra story here. Let me perhaps take this example. So for every simply laced linking diagram, Etinghoff, Oblomkov, and Reins introduced some generalized double affine Hecke algebras. And then they proved that by considering the spherical subalgebra and taking the semi-classical limit, you obtain exactly this polynomial and with its, so the zero set of this polynomial. And the same also for the double affine algebra of rank 1. This was a result by Oblomkov. If you take the spherical subalgebra in the case Q equal to 1, it gives exactly the Pine-Levé 6 or the character variety of a Riemann sphere with 4 holes. Okay? So conjecturally, and this conjecture appeared also in the paper of Oblomkov and Reins, you would expect that corresponding to this elliptic singularity of type E6, there should be an elliptic Daha such that the spherical subalgebra of that elliptic Daha for Q equal to 1 gives this polynomial. As we go down the list, I would expect that we can obtain some Dahas coming from the generations of the generic the general double affine algebra of type E6-1 to describe these two polynomials. And as we go down from here, we keep going, and these are going, so from the double affine algebra of rank 1, in a paper in 2016, I introduced some degenerations of these algebras such that every time you take the spherical subalgebra, you take the classical limit, and you go down your list of the Pandey equations. So I'm not going to tell you this story because it's long now, but thank you very much. I think I took enough of your patience.
Well, thanks a lot. Let's thank the speaker.
Thank you.
So are there any questions or comments? You can either unmute yourself and ask a question, or you can also raise your hand, or you can pose a question in the chat, whatever you prefer. Yeah, Marco.
Okay. Thanks for this this talk. I love all these algebras. They're amazing. So I just wanted to ask a couple of questions. So when you deform the standard part of the polynomial to add lower order terms, are you saying that it's not, so we should not kind of homogenize and express these as hypersurfaces inside P4? Like, are these related to the Skleanin algebras of the one higher dimension?
No, not
Okay,
as far
so-
as I know.
Okay.
No, so essentially, because I'm writing this, so the polynomials we consider are in C3. So when we complete them projectively, they are in P3 naturally. So there is the case, I should say that if you consider the case of the elliptic singularities of type E8 and E7, then you will find higher powers in these terms. But those are actually completed not in P4, but they are completed instead in the weighted projective space P3.
I see.
So I don't know how to go to P4.
So, okay, and this double affine Hecke algebra, so you said that the relationship between that algebra and the ones you're considering is that you took a spherical subalgebra, and this is associated to a central idempotent.
Yes.
Do they have, I don't know much about the Daha, so do they have only one such thing, or?
No, but they are, you can do it in many ways, of course.
Yes.
But they are essentially related to each other by some automorphisms.
So, sorry, this is not a central idempotent, it's just an idempotent.
So that means that, I mean, is there?
Yeah, you make it
does
central
Daha-
in the spherical subalgebra. That's what Marco meant, I think. That
In the
you
spherical
take an
subalgebra,
idempot- you
in the
take-
spherical subalgebra, it will be the identity.
Yes. And it's central, therefore, right?
Yes.
Okay, but I'm just wondering, so the parameters that you're seeing in the second column, are they related to the choice of the idempotent, or are they related to the choice of the Daha?
The choice of the Daha.
I see. And what's the, so if the second column is to be interpreted as some kind of deformation of a character variety, like an affine character variety, what is supposed to be the interpretation of the Daha?
Haha. Okay, so for this guy, the Daha is really, I actually presented a small result in which I showed there is some sort of natural interpretation of this Daha as the quantization of the group algebra of the monodromy group of the Pauli-6 equation, or in other words, of the group algebra of the holonomial, if you want.
Of the cusp thing? Of the cusp?
No, this is non-cusp yet.
I see.
Cusp is here. So in this case, this is the case of a sphere with 4 boundaries. So it corresponds to the isomonodromic deformations with 4 simple Fuchsian singularities. And then you take the monodromic group, then you take the group algebra of that, and you quantize it in a natural way, and you obtain exactly the C1, check C1 Daha.
So that means that you're not imposing the the relation which defines the moduli space. You're only using the group algebra of the fundamental group.
I'm only using...
I just mean that okay, you're saying that it's the group algebra. I see. I understand. Thank you.
Yeah.
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 More questions or comments?
Well, I mean, it's a group algebra, what you mod out by quadratic.
So there are relations, yes.
In Pinleve case, quadratic relations for generators, and in the E6 case by cubic relations for generators.
Yes, sorry, yes. Essentially, Marco, when you know these parameters here.
So essentially it's a Hecke algebra of a certain type.
Yes, so these guys are the ones which essentially appear into your Hecke relations. Related to the ones which appear in the Hecke relations. Correct?
Yes.
Okay.
This is Andy Hone. Hi. Can I ask about this Halfman divisor?
Yes. Okay.
I see you have the cubic surface defined by phi equals 0, and then you say the del Pezzo divisor d infinity that defines another cubic surface, and then you intersect the two things. So then that gives you a curve, which gives you a divisor on the surface you started with, right? So is that the Halfman divisor?
It's a little bit less straightforward. So for the first part of the table, that's definitely the case.
Right.
Until sort of here.
Right.
Then it becomes more complicated.
Because everything's very singular.
No, there is a little bit of... Okay, so the way in which we associated this column of Alfvén divisors is by using a result of Sakai. So in the first part, definitely what you described, but in the second part of the table, this is the Riemann-Hilbert correspondence. So because from the blue line downwards, we have the differential Pandey equations.
Yeah.
And therefore, so all of these are the monodromy manifolds. And these Alfvén divisors, they tell you about the initial condition space for the Pandey equation. And so if you want, like, this double line is a Riemann-Hilbert correspondence.
Right. So it's and above the line that corresponds to difference Pandey, is that right?
Yes, those are multiplicative discrete Pandey equations.
Multiplicative discrete. Okay.
So so in the case of the additive discrete, the problem is that they don't lead to Calabi-Yau algebras.
Okay.
In our construction. Okay, so we still have a similar situation, but they don't lead to Calabi-Yau algebras.
Do the algebras have any nice properties, or? those cases?
They are very simple.
They're just very simple.
I just, I don't know, to be fair, if they are of any interest.
And what, sorry, remind me, so what does the Halfin divisor represent in the Painlevé theory?
So you see, so the initial condition space in the Painlevé equations is given by taking P2 and blowing up 9
Blowing
points.
up in these points.
9
points, yeah.
Which are not in generic position. And so, for example, let me take this example here. We have that these points, they lie, well, of course, given any 2 points, they lie on a line, but in this case, we have the 3 points lie on the line, and there is a triple point.
A triple point, right, yeah.
Yeah, here is a triple point, so let me put the number 3 here. Here we have a quadruple point, and here we have 2 points of order 2, so it always adds up to 9. So this is order 5, right? 5, and so on.
Okay. Thank you. That's helpful. Thank you.
No problem.
Yeah. More questions or comments from Marta? Well, if not, thanks again.
Thank you very much.
So we close this session, and next time, in a week from now, we'll have Rayo Shemar speaking at Global Poisson. So please come. So thanks a lot, and thank you again.
Thank you.
Marta,
Thank
can
you.
you stay on for a few minutes so that we can ask more questions after?
Yeah, sure,
everyone
of
is gone?
course.
Okay, great.
Okay, well, thanks. Bye.
Could you share your slides again?
I will stop
I could
the
start
YouTube
relaxing.
live.
Oh, okay.
Thank you. So I was almost ready to start my GNT.
Well, there's nothing. You shouldn't let that stop you. My questions will be compatible with GNT.
Okay, great.